Well, good morning. This industry don't seem to be able to standardize on anything, but every company I've ever been in have always tested a fire alarm at 10 a.m. on the first date of the month. So at least somebody knows how to standardize. Yeah. So one of the benefits of being in this role is that a lot of people they try to give me tips on how to introduce. And one individual said this morning, you should ask them why you're all here today. And I said, why shouldn't they have been here today? Well, something happened yesterday. And I said, what happened yesterday? So that's how interested I am in football. But anyway, congratulations if that matters to you. I'll take you back a little bit. I'll start with that. So imagine this. Imagine that there is a room or a building filled with books. Millions and millions of volumes. Hundreds of millions and billions of paper. But they're all locked away. They're all in their own separate small rooms. They're all tended to by librarians who care about their particular room. They're organized in a hierarchy where all the librarians are connected into a structure. And there's a chief librarian caring about the entire library. But the problem is they keep a very strict access control. It's very difficult to get in and out of these rooms. It's like the old library, right? You had to check in your books and then you were handed it and you had 14 days or whatever and you had to hand it back, and if you didn't hand it back you would get a note and you would get fined if you didn't hand it back, right? Imagine that. For years that was the actual oil and gas story. Functional silos tended by people who really cared about their data, and they meant their data as in I am in control of my data and don't ever touch it. And they were organized in hierarchies with other librarians who felt the same way. The problem was that there was a whole host of these libraries inside something called companies, and none of them ever discussed that they were certainly not lending their books away. This is the reality in 2016 when we started this project. We tried to fix this in 2016. We made a slogan called Data Liberation Front. I see some of my colleagues in Cognite are still wearing the t-shirt. That means that the fight is still on. It's not won, not yet anyway. So today I'll start with tell and show. What's another show and tell maybe? How we focused on industrial data over now close to a decade, and what that actually means as we're now taking a step into industrial artificial intelligence. Then I'll try to dive into this architecture, where architecture starts mixing in with the functionality that are now being released by artificial intelligence. And I'll show you a case example where we use root cause analysis, not too far removed from your example. And then I'll try to underscore the importance of actually getting this right, not just for the simple companies or the single companies, but for the whole industry, because the problem now is that we can't win alone, we have to win collectively. Or ultimately fail collectively, but today we don't talk about failures. So I'd like to start with the basis for data liberation. First, you need data. But there is loads of data. But you need the right data, the good data. And the good data with the right quality control, the right lineage, and the right versioning, so that you know you're working on the right version, right? Anybody ever worked on the wrong version? I know I have. Second, you need to make it accessible. Because critical operations, like you just saw in the demo, that need timely insights. You can't wait days if your timeline is minutes. You can't expect to have results without talking about call it multiples of productivity if your data platform is not delivering the data and you need to have a conventional system of accessing the data. And then accessible data power insights, systems, applications, workflows, and ultimately artificial intelligence powered work systems. And thirdly, we understood at that point that consistency in this data platform was essential. The industrial tech stack was significantly more complicated than the retail part of it. And we took people from Google Engineering, which they felt were pretty sophisticated. They had a look at the industrial tech stack, and they came away with a little bit of an amazement in terms of complexity. Because it's not just that data was complex, but the vendors were also competing for control, resulting in inaccessible data. They were competing for market shares, they were competing for commercial models, all of it resulting in barriers to data accessibility. And even more critical, as this demand grows, these functional barriers become almost impossible to overcome. Today, we have a way of actually doing this that scales across assets and sites, but it says a really strong requirements into the call it non-data part, the librarian part of data management. And fourth, we tried to create, we're not yet there, but we tried to create a digital ecosystem for what you call seamless data flow. So I no longer talk about data accessibility, I talk about the flow of data. Think about like a river. Data is like water, right? Usually running with gravity, and it gathers into streams. The same idea you should have about data. It basically flows, it needs to flow. And that thinking, that single source of truth type of thinking, that interoperability, interaccessibility, interstructural capability resulted in a trusted data foundation. One single source of truth, and that supports decision-making in a timely fashion and allows us to create a data platform that everybody can access to. So now you have control over versioning, you have control over lineage, you know the data governance, everybody has a common source of truth, so everybody knows the same information or same data at the same point in time. And now you actually created a basis for a lot of what I will talk about later in terms of artificial intelligence, concurrent engineering, etc., etc. The problem is that the librarians are out of work. And librarians don't like to be out of work. So they are fighting back. And maybe we're smart doing this. And I'd like to think so. But honestly, I think we were probably lucky. Because right now, the structure that we created, the drawings we created back in 2016, are leading us into the age of artificial intelligence. And there's a lot of talk about where to invest in artificial intelligence. I'm guessing you guys have lots of companies coming to you with all sorts of smart ideas around artificial intelligence and where to invest to gain value. And you probably have lots of consultancy companies coming to you trying to provide advice of where to invest in artificial intelligence. I think that's really interesting. Consultancy companies coming you to advise on the use of the technology that will make them redundant. I think that's a perfect example of the world. But if you haven't placed your bet, and if you don't have your data under control, I have one piece of advice. make sure that your data platform is AI ready. Make sure that it is connectable, that it's interoperable, and if you have the possibility, information graph seems to be the industry standards. Because right now, we're actually moving beyond digitalization. AI, to me, is not just another tool, and I'll talk about this later. It's fundamentally a tectonic shift in how we think about consume of data. So we're no longer talking about applications powered by data guiding decisions. We are talking about machines making decisions by themselves, consuming the same data, and then creating new information that are in turn being consumed by other agents. So this one goes from being connected to being integrated, native, embedded, seamless. So that you kind of moved up one division. The problem is that without this data, AI is basically useless. So while people is investing a lot of money and effort into, call it, the application side of artificial intelligence, which is the prompting, the interfaces, the human-machine thing, they're forgetting their data, and they're getting useless results. But as AI is on the verge of disrupting not just the application space, but frankly, the whole way we think about work processes, and by thinking about work process, how we also structure our companies, this data becomes even more essential. The understanding of the data becomes even more essential. So maybe the librarians aren't out of work, they need to find different work. In Aker BP, we built what we call the North Star architecture. To us, it's basically a blueprint for the future. And it's done by consolidating different platforms, Cognite Data Fusions, or CDM now for the operations data, Microsoft Fabric for everything that is outside, ERP systems, and all the office systems, etc. And then ADME, which is basically an instance of OSDU, into one interoperable system. Two important criteria is to try to base that on modern, call it self-reinforcing data architectures, like the information graph, but also making sure that we're tapping into these megas and hyperscalers' way of thinking about their information systems, because they are investing massive amounts into these systems because they want to take the benefit of artificial intelligence, but also making sure that these data are actually interoperable, that they actually flow. And in these three systems, CDM, Fabric, and ADME is basically covering our entire business system. Almost all data we have, with very few exceptions, will be in one of these three systems. So if you can connect these three systems through APIs or other connectors, you basically have an interoperable systems. But then you also need to enforce industry standards. This is really complicated, guys. The problem is that technology is moving far faster than these standard and protocols and all these kind of communities and committees and God knows what not are actually moving. So the standards are beyond, way behind the technology front. And then you need to put these data into systems like the digital twins you just saw that contextualize the data. So the data in itself is fine, but then you need the information, the metadata, the stuff that actually connects the different data. They can be semantic models, logical models, arithmetic models, they can be transforms, and they can be a mix of all of the above. The simple way of doing that is of thinking about it like a graph where you actually build out the nodes depending on what kind of models you need. So you can have very simple models for very simple problems and extremely complicated models for extremely complicated problems. The reason you really want to do that is you want to move from proactive, which you just saw, to predictive. And in order to get to predictive, you need to have the logic. You need to understand how one signal impacts a lot of other signals, not just in past, but also in the future. And why does all of this matter? Why all this talk about data? Because the AI-ready data is not just yesterday's data. It is structured, it is standardized, and it's enriched. Because the machines are going to, in the future, do a lot of the reasoning that we as humans do. The human brain is a fantastic, not an invention, but it's a fantastic organ. It allows us to see patterns where machines can't see patterns, but AI is changing that. So imagine this. Instead of searching for a document, you use some sort of query. You query a graph-based models, and you discover, it's like you just saw, relationships that you didn't even know existed. And not even that, you get also a ranking of this relationship based on some sort of semantic or logical model that creates a probability map of where the relationship are strong or weak. The PNID you just saw is rather simple. In big platforms, there can be thousands and thousands of these connections, and it can take days and weeks to understand the different connections. In contextualized data, where the graph is basically showing the relationship, a simple query can reveal all of these connections in one simple search. Another example, and this is real. When you're running drilling operations, a lot of what we're doing now is modeling based. All of these models are actually empirical models. So that means they're actually taking on board what have happened in the past. Some of them are mathematical in nature, but all these equations are actually empirical adjustments to actual data. The problem with the good thing about the empirical model is that interpolation is really good. The bad thing is that extrapolation is generally mathematically not acceptable. So they're not predictive. So when you move from these kind of empirically based mathematical models to agentic workflow, you're taking on board the context, you're taking on board the physical relationship, but you're removing yourself from the mathematics. And that means you can actually now do extrapolations. You can do adjustments in real time, adjusting parameters like ROP or weight on bit or whatever in seconds. Humans don't even see the data on the dashboard before the agent have adjusted the data. That brings me to another concept, and you've seen it before. So in the digitization area, you had APOS. Everybody knows what APOS is? Work process-based modeling, right? So you had people, machines, systems, decisions, right? You have input data, you had processing, and then you had output data. You have probably seen thousands of these. And you can think about this like an assembly line for decision making. It is basically a cookbook. So you could look up in that cookbook, you could follow the rules. Some organizations have systems where you actually have to tag off that you actually follow that and made the consideration. There are requirements and best practices and God knows what not. And every time you make a mistake, there's a new one. So it grows. But these assembly lines in the age of AI, they actually break down. So the humans are essentially removed, and then the humans are basically governing the agents. So you go from sequential work processes into concurrent set of agentic workflows running in real time. Because they don't wait for your instructions. They have a tendency of acting. And you don't need to be a maintenance engineer to optimize the maintenance programs if you have a robot that is called Yggdrasil maintenance operations. Everybody can run that prompt if they have access to it. So this means that organizations change. because the functions are no longer executing the task. The functions are caring about and training the agents and putting them into workflows and ensuring that these agents put out the right results. They are training their agents. They're not playing anymore. Governance becomes critical, right? Because if everybody can run an agent, and they have no clue what the result may or may not be, then the governance of these models become critical. And then leaders, like myself, we are probably the last generation of leaders that actually only have human employees. What does that mean in terms of leadership, in terms of organization, in terms of structures, in terms of contract, in terms of how we interact with the ecosystem? Truly, I don't know the answer to that system, but the last question, but we are experimenting in Aker BP. We're trying to figure it out. Very simple words. Think of it like this. In the digital world, we were building a road. We were trying to make it as straight and as wide as possible, making the cars flow as easily as possible, making on and off ramps as accessible as possible, making sure there was absolutely no queue. In the AI world, the road is gone, and we're all flying, unmanned. Because agents don't wait for documents and approval. They stimulate, they predict, and they can even act without human interference. One such example. And this is basically talking about the collapse of the human digital workflows. So this one is a very complicated case. It's called root cause analysis. It's what happens when equipment has a tendency of breaking down. And sometimes it's simple. It's a bearing. Machine learning has detected increased vibrations. You're pretty certain that this is the root cause. You go out, change the bearing, run it up again, and it's all honky-dory. But if you have a very complex case, and gas processing is one of these cases, there are lots of different things that can go wrong and actually do go wrong, and they go wrong at the same point in time. Traditionally, I don't know how it is in Equinor, but we run, I don't know, less than 50 of these cases a year. They take weeks, 6, 7, 8, 12 weeks is not abnormal, which of course you can't wait for if your facility is down, so you basically change everything. You call Aker Solutions and Able, you get a crew together, and you change everything you possibly can, because the cost of actually having this plant down is so huge that you can't wait for root cause analysis. The experimentation that we've done now show that this root cause analysis, this specific example, and we took real examples, real data, and we hid it from the team that was going to do it. So we knew how long it's actually taking conventionally. And then we deployed agent and data builds and all of that stuff to try to do it. Up to 97% faster. On actual data, on actual experiments. The one thing we learn is that this ability to get data together was far more complex than we thought. So data modeling was actually the most time-consuming aspect of root cause analysis. To me, that was a bit staggering, actually. We spent more time modeling the data and getting it into a consistent data model than anything else. That tells me that the better your data models are, the faster this will actually be. The problem with data models is that, yes, there is a certain industry standard, but we as an industry are really, really poor at sticking to these standards. So maybe we do 75% standards, and then the 25% we think, maybe not, we'll do something else. Could be that 25% was really, really important. And the second one was that we ended up with far fewer false positives than I had assumed. I had assumed that this would be an iterative approach where you ended up with lots of false positives that you checked back and then came to another conclusion. That wasn't the case. The problem was the data quality. The actual data quality, because the humans who actually done these cases, they had washed, massaged, taken out their erroneous data, etc., just like you demonstrated. Sensors that should have been changed but wasn't changed was still in the system. And when you're running these kind of data models, you don't detect it. So creating agents that actually picks out illogical data is probably an important, call it pre-processing step. And then human bias was really, really important. The thing is that these guys who know these assets, they think they're unbiased, but they're extremely biased. They know more than they know. They know more than they talk about. So they have this intuition of where something may or may not be wrong, which is really, really important when you're projecting it into something like a root cause analysis. The problem is replicating this bias with agents that basically are biasless. So what are these improvements in a way? What is actually driving us to do this? Well, time reduction, you've seen. Automate the data collection and contextualization. We really believe that we need to create more precise data models, more contextualization. We need to make rule-based type of engines. They could be semantic, logical, arithmetic, transform-based, I don't care. But we need to make it on the fly. We need to automate these workflows. And we believe that there needs to be a fundamental increase in what you could call advanced pattern recognition, trying to take out the biases, trying to learn from this pattern recognition that we as humans have basically ended up with. We need to go from reactive RCA to proactive RCA. We need to try figuring out what is about to happen before it happens. And we're trying to move into using Gen AI, or you could call almost AGI type of thinking, or now really a set of agents working together to look at recommendations and decisions. We're actually live in subsurface now, because another area where there's lots of bias is exploration. They don't believe it themselves, but they really are highly biased. And being aware of that bias, because the agent is biasless, so it actually tells you, well, here you're biased and here you're not biased. It's actually live today. I believe this is having a fundamental industrial impact. It'll change everything. But it starts with data. So a little call to action. When we started out back in 2016, the whole ambition was to make sure that we have a consistent data platform. I think that is foundational, fundamental, and something we just need to adapt to. But we can't act as individual organizations. We need to start acting like ecosystems, where all these different organisms are really fundamentally dependent on each other. And the price is huge. The difference between the upside case and the downside case in Sodier's stipulations are 15,000 billion NOK. And even on a Monday morning in Stavanger, that's a lot of money. I used to say to my organization, and I call it a small organization, because I think the first error we can make is to make our organizations big, because then we introduce the bias of structure and burden and bureaucracy. I hate bureaucracy, positively hate bureaucracy. I think there are three things we need to do. 3 simple tasks, but 3 really, really complicated tasks. 1, we need to start with our operating assets. And we need to set much higher standards for the operabilities of those assets. We need to basically lift the performance requirements out of a category where the humans can't do it alone. 5-10% increase in production efficiency sounds great, but in reality it's 1 or 2% increase. What do you say if you say, okay, I'm going to operate, take away planned maintenance, that's the separate category, I'm going to operate my assets company buys at 97%. Set that standard. And then subsequently, we need to continue developing the existing projects on time, within budget, and with much higher quality than we've done in the past. So we need a fundamental productivity increase in projects too. And finally, to actually do this, we need to develop more, discover more, develop more, and we need to do it a lot faster than we do today. A lot faster. 3 simple tasks, but also 3 really, really complicated tasks. The problem is the way we've done it in the past in this industry, improving a few % per year, is not going to cut it, guys. So I've set the target internally to really step out of our comfort zone to do 3x. 3 times the productivity. Productivity defined by all input factors, inclusive of time, that is necessary to produce a barrel of oil over that barrel of oil. And then you can use whatever denominator you want. You can calculate back to money, you can calculate the time, you can calculate the FTEs, you can do whatever you like. 3x productivity. If you really want to break it down, field development needs to increase by a factor of 2, and cost needs to come down with about a factor of 0.5. The only tool that I see it's possible to make these kind of efficiency gains is the radical and widespread use of artificial intelligence. But that comes with complications. We can't do it alone. You can't do it alone. The industry needs to decide that we need to do this together. That's why I'm here today. This is a brilliant example of 4 of the biggest and most forward-leaning companies coming together to solve a problem. The problem is that the world just got more complicated. So what we've done in the past is not good enough. We need to do it again, and we need to do it a lot faster. The good thing, we're all in the same boat. The bad thing, if that boat sinks, we all drown. Thank you, guys.